Before we write our first monetary policy, our first minting policy, let's briefly recall how validation worked that we have seen so far. So when we don't have a public key address, but a script address and a UTXO that sits at such a script address and a transaction that tries to consume that UTXO as an input, then for each such script input, the corresponding script is run, the validation script. And that validation script as input gets the datum, which comes from the UTXO, the redeemer, which comes from the input, and the context. And here we can see the context again. Recall that's in package Plutus minus ledger minus API as well in the module plutus.v1.ledger.context. And so it's defined here. And it has two fields, the txinfo field and the script purpose field. And we saw that for script purpose, everything we have seen until now always had the purpose spending txoutref, where txoutref is a reference to the UTXO we try to consume. And this txinfo has all the context information about the transaction that is being validated. Now for monetary policies, for minting policies, this is triggered if the txinfo mint field of the transaction contains a non-zero value. In all the examples we've seen so far, this was always zero, which means in the transactions we've seen so far, we never created or destroyed tokens. But if this is non-zero, so we have a value here, then this value, as we have seen just now, can contain a bag of asset classes, so different asset classes for different currency symbols and different token names. So if this is non-zero, then for each currency symbol contained in this value that is being forged, the corresponding minting policy script is run. So each currency symbol is the hash of a script, of a policy script, a minting policy script. And for each value that appears here, for each currency symbol that appears in this value in the forge field of the transaction, the corresponding script that belongs to the currency symbol is executed. And where the validation scripts had three inputs, the datum, the redeemer, and the context, these minting policy scripts only have two inputs, a redeemer and the context, no datum. That would make sense because datum sits at something that's being spent and the output. And in this case, there is nothing like that. There's no place where the datum could possibly sit. So the transaction will provide the redeemer, as it also provides the redeemer for all script inputs. So for each currency symbol in this value with a non-zero amount, the corresponding minting policy script will be run with the redeemer and with the context. So the context will get as txinfo the transaction that's being validated, and as script purpose it will get minting with the currency symbol that is currently checked. So whose minting or burning is currently checked. So to be precise, we look at all currency symbols that appear with a non-empty map in the txinfo mint field. So all currency symbols where there is a token name, so that's the corresponding amount to that currency symbol and the token name is not zero. And for each of those currency symbols, we run the corresponding policy every time with a different script purpose, namely minting that currency symbol. So there may be several different policies involved in one transaction if you mint currency of different currency symbols in this transaction, mint or burn. And for each of those currency symbols that are involved, the corresponding minting policy will be executed. And they all have to pass. If only one of them fails, the whole transaction will fail. So let's look at an example of a minting policy. And let's start with a very simple one, similar to what we did for validators. I created a module free, and as for validators, we first define a Haskell function that represents the policy, and then we'll compile it to Plutus core. So a validator takes the datum, the redeemer, and the context. And as I explained, there is no datum for policy, so we just have redeemer and context. And for this simple one as redeemer, we can use just unit. And then script context as before, and again bool. So this is the typed version. So I mentioned before that there's low-level Plutus, which just uses data or built-in data for all arguments, and then returns unit, and failure is indicated by throwing an exception. But we won't bother with that here and immediately use the typed version. And normally I would need a toData instance for the type of the redeemer, but unit has one already. So the simplest policy we can write is the one that always returns true. So no matter the script context, we just return true. So this represents a minting policy that allows all sorts of minting and burning for the currency symbol given by this policy. Recall, the currency symbol is the hash of the script. Next, we have to compile this policy to Plutus script. And I call it the result policy, so it's of type minting policy. And very similar to what we do for validators, there's a function called make minting policy script. And then comes template Haskell. And again, we use compile and Oxford brackets. And here it's slightly different to what we do for validators. So we take our policy, our Haskell function, but that still has to be converted to the untyped version that just uses built-in data for the arguments and a unit return type. And this is what wrap minting policy does. So as before, this wouldn't work because in these Oxford brackets, everything has to be inside them. So we can't have external definitions except if they can be inlined. So again, we have to add this inlineable pragma. So let's do that. Inlineable make policy. And once we have the policy, we can get the currency symbol by using the function script currency symbol applied to the policy. I should mention that similar to how we have parameterized validators, we can also have parameterized policies. So there could be additional arguments here in front of that, the parameters of the policy. So if I start the REPL and load that module, then the currency symbol should be available and I can actually look at it. So this is now the hash of the script that we got from compiling the Haskell function that represents the policy. So that's the first currency symbol that's not ADA that we see. Going back to the editor, this completes the on-chain part. So we define the policy as a Haskell function, compile it to Plutus script, and we can also derive the currency symbol from that. But in order to try it out, we also need an off-chain part. So I prepared that already. And the idea is that we will have one endpoint called mint that takes as parameter the token name and the amount we want to forge, respectively burn. So if the amount is positive, we will forge, and if it's negative, we will burn. We only have to specify the token name because the currency symbol is given by this script. So the off-chain function in the contract monad, it takes these parameters. Then first we compute the value that we want to forge or burn. So we use the singleton function that we saw before. Currency symbol is our shining new currency symbol. And we extract the token name from the parameters and the amount. Then as lookups, we have to specify the minting policy. So the transaction has to contain the actual script, the minting policy, the policy itself for validation to be successful. And the only constraint we put on our transaction is using something called must mint value, which is self-explanatory. So this transaction must mint the value we computed before. Then when we submit, so when we use submit TX constraints with these lookups and that TX, then the algorithm will automatically take care to find an input in the wallet to cover the fees, and it will automatically transfer the minted value to the wallet if it's positive. If it's negative, it will try to find sufficiently many tokens in the user's wallet that can then be burned. So we wait for confirmation and log a message that we forged this value. So then we define the endpoints as before. So we just call mint and then recursively endpoints again. And mint prime is just using our mint, but using the endpoint function to actually expose an endpoint and then feed the parameters into the mint function. So this is boilerplate so that we could try it out in the playground. And additionally, I also defined an emulator trace. Since the last lecture, we know how to do that, so we don't have to test it in the playground. We can also just run it on the console using emulator trace. So I define a token symbol, TN, token name. Then I run these endpoints, so the endpoints contract in wallets 1 and 2. So I start them. Then I call the endpoint mint on wallet 1, where I use this token name and I mint 555 coins of that token. Then wallet 2 mints 444 coins of that token. I wait one slot, and then I, on wallet 1, burn 222 tokens. So in the end, wallet 1 should have 333 and wallet 2 should have 444. And I wait another slot. I should still mention that here in the must mint value function, I'm just mentioning the value and not the redeemer. And that is because the case that the redeemer is of type unit is very common, so there is special treatment for that. So back in the REPL, we can reload and try out to test. And we see these must be wallets 1 and 2. So this must be wallet 1. So first 555 were minted, then 222 were burnt, and 333 remain. And this must be wallet 2, where 444 were minted. We also see that both wallet 1 and wallet 2 have slightly less ADA than the other wallets because they had to pay transaction fees for the minting and burning. Finally, let's try to recreate exactly the same scenario in the playground. So I already copied the code here and compiled and prepared the scenario. So we have two wallets, and wallet 1 and wallet 2 mint simultaneously. Token name ABC. Wallet 1 mints 555. Wallet 2 mints 444. Then we wait for one slot. Then wallet 1 calls the mint endpoint again, but this time with a negative amount with 222 burning. And we again write a slot. We evaluate. Then, as always, this is the Genesis transaction that gives the initial 100 ADA to the two wallets. Then here, let's see, it's 444, so that's wallet 2. The minting by wallet 2. The 100 ADA go in, 2,533 loveless fee. The rest goes out, except here is another UTXO containing the newly minted 444 tokens and an additional 2 ADA. And that is due to something called min UTXO. So in Cardano, UTXOs must have a minimum value. So in the playground, this value is 2 ADA. Therefore, it's not enough to just have these 444 tokens. Additionally, there must be at least 2 ADA. Then the other transaction that happens at slot 1 is the same for wallet 1, and now we mint 555 tokens. And you can also see that minting happens, minting or burning, in the middle in the transaction, here in this forge block, where it mentions the currency symbol or policy, the token name, and the amount. And finally, in slot 2, we see the burning. So here inputs are ADA UTXO and the one holding the 555 tokens, and these min UTXO to ADA. Then the transaction burns 222 tokens, and we have one UTXO output, the remaining ADA, and 333 remaining tokens. So we can also check the final balances. And in the diagram, we don't see the token because it's so small, the amount in comparison to the 100 million Loveless. But here in the table, we see it, that wallet 2 ends up with 444 and wallet 1 with 333, exactly as in the emulator trace. So this is our first example, complete walkthrough of using native tokens with Plutus, our first minting policy, and it's a maximally permissive policy that allows arbitrary minting and burning with arbitrary token names for this currency symbol.